In this video, we're going to talk about independent events. Independent events. And again, this means the events that do not depend upon other events in the sense that the probabilities don't change no matter what other events have occurred. For example, if you flip a coin, the probability you will get a head is 0.5, assuming the coin is a fair coin. It doesn't matter how many coin flips there were previously, and you could have had maybe 10 heads in a row up to this point. Yet when you flip the coin again, the probability of it being hit is still 0.5. So this is an independent event. In other words, this flipping of a coin is not dependent on anything that has happened previously. Now let's consider something else. Let's consider this example here. So you have a bowl. With 3 red and 4 blue marbles. And so let's call, so suppose, let me say it this way, suppose you choose a marble at random. And you get a red marble. And let's call this event, let me give this event a name. Let's call this event E. You choose a marble at random and you get a red marble. And you do not put it back. And then event F, you choose a second marble. And get a blue marble. Now, events E and F are dependent on each other. And in particular, so let's say, what's the probability of event F occurring given that the event E has occurred? This is something we did in the last section, but we're going to do this sort of with numbers now. So you're assuming this event E has occurred, you picked a marble and you got a red one. And now, from what's left, you're going to pick a second marble, and you want the probability that you're going to get a blue one. Okay, there's 4 blue marbles. in the bowl. And you've already taken a red one out. So the probability is going to be that 4 divided by 4 plus 2 is 4/6 or 2/3. So that's the probability of you getting a blue marble on the second try, given that you got a red marble on the first try. Now let's calculate the other way. Suppose you did not get a red marble on the first try. So suppose you got a blue marble on the first try. So that would be the case where you did not get a red marble. Let's call that E complement. And so the probability of event F occurring, given that E complement has occurred. So what do we have? So if we got a blue marble on the first try, that means there's only 3 blue marbles left out of a total of 3 plus 3, which is 6. So that's 3/6 or 1/2. So we would say in this case that event F is dependent upon event E, in the sense that the probability, I meant to put an F in here, event F is dependent upon event E, in the sense that depending upon how the outcome of this event was, will affect the probability of this event. So now, in the case, suppose you have 2 events A and B. We say A is independent of B if the probability of A given B is equal to the probability of A. In other words, if you calculate probability of A given B, and that's the same as the probability of A, that means that A is independent of B. Because you see right here, normally we would have probability of A intersection B divided by probability of B. But if this is just equal to probability of A, that's saying that it really didn't matter what happened here. The probability of A did not change at all. Same thing, we say B is independent of A if the probability of B given A is equal to the probability of B, like that. So once again, the probability of B doesn't change even if A has occurred or not occurred. Now, another way to say this is two events A and B are independent if and only if the probability of A intersection B is equal to the probability of A times the probability of B. They're independent if and only if this is true. And note, normally, let's say if we had, remember, probability of A given B was equal to probability of A intersection B divided by probability of B. Remember that was our basic formula. But if probability of A intersection B is equal to probability of A times probability of B, then what does that mean? We plug this in, and over here, we're going to put this. And these cancel. So we get the probability of A given B in that case is equal to probability of A. And so once again, you can see here, this implies that A is independent of B. And then also, probability of B given A is equal to probability of A intersection B divided by probability of A. But once again, but if probability of A intersection B is equal to probability of A, probability of B, we have probability of B given A, and plug that in right here. It's going to be probability of A, probability of B, probability of A equals the probability of B, like that. And so we can use this information here to test if events are dependent or not dependent. So let's do this example. In a certain computer, the probability of a CPU failure is 0.02. The probability of a power supply failure is 0.01. The probability of both failing simultaneously is 0.0014. The question is, A, are the CPU and power supply failures independent? B, suppose you discover that the power supply in the computer has failed. What is the probability that the CPU has also failed? Now remember our test for this part A, our test to see if they're independent is to find the probability of the intersection of the two and see if that is equal to the probability of the each of these multiplied together. So let's check this out. So solution. So remember, we're given that the probability of the CPU, let me just say CPU for CPU failure is 0.02. Probability of power supply, let me just call that PS, power supply failure, is 0.01. And we're also given the probability of the two failing simultaneously, that'd be an intersection, is 0.0014. So let's do part A. Let's test this out. If we multiply CPU, probably CPU times probability of power supply, and we multiply this times this, we get 0.0002. Now notice that's not equal to the probability of this intersection. So the probability of CPU times probability of power supply is not equal to probability of CPU intersection power supply. So they are not independent. Of course, what that means is they are dependent. So the probability of one failing will change the probability of the other failing. And then again, so for part B, we were asked, suppose that you discover the power supply in the computer's failed with the probability that the CPU has also failed. The probability of CPU, given that the power supply has failed, is going to be PCPU intersection power supply. Remember, divided by the power supply. That's going to be 0.0014 divided by 0.01, and put that in your calculator, get 0.14. So the probability of the power supply failing, probability of the CPU failing, given that the power supply has failed, is 0.14. So it's actually increased because in general, the probability of the CPU failing is 0.02. But if we know the power supply has failed, the probability of CPU failing is 0.14. Of course, we did problems like this in the last section. What we're just adding now is this question of whether or not events are independent of each other.